Hey everybody, welcome back to Extreme Math, episode 3. This is going to be the conclusion of a two-part series on the Baire Category Theorem. I can barely contain my excitement. Now, the Baire Category Theorem is a very important theorem that appears everywhere in math. It can be used in topology, functional analysis, and many different areas. And so, before I start proving it, let me go over a few definitions really quick. The first definition I want to go over is first category. Now, I mentioned it in the last video when I talked about the Banach Mazur game. And so if you haven't done so, please go and watch that video because it's going to be a prerequisite. First category, as we mentioned, refers to a set that is a countable union of nowhere dense sets. And so nowhere dense, as you remember, it means that for any interval, there's going to be a subinterval that does not contain elements of that set. The second definition is second category, and that's pretty simple because any set that is not first category will be a second category. The third definition is a residual. It's also pretty simple. A residual will just be the complement of a first category set. And so now we can get to the heart of this video. The definition of the Baire Category Theorem is that every residual subset of R is dense in R. And so if we can show that every residual will be dense, then we have proved the Baire Category Theorem. And I do want to mention, if for some of the more advanced people, that there are different definitions of the Baire Category Theorem, and you might have seen it expressed differently, but they should be equivalent. Okay, so let's get started. In order to show that a residual is dense, we have to show that for any interval that intersects the residual will contain an element of the residual. And so to express this mathematically, we can show that if you say that X is a residual, then when it's intersected with an interval from A to B, then this intersection will contain an element of X. And so how do we prove this? Well, we're going to be using an interesting proof method. It's not going to be by contradiction. It's not going to be by induction. No, this time we're going to be talking about proof by game. I bet you haven't heard that one before. And so what game are we using? Obviously, we're going to be using the Banach Mazur game that I've been talking about. And so how do we play this game? Let's say that we're player A, and this time we're given the set X as our set. And so this set, as we know, is a residual. And so by definition, the complement will be a countable union of nowhere dense sets. Each of those nowhere dense sets will be represented by big Q sub n. And so if we begin playing this game, we have to choose a closed interval. And which one do we choose? Well, the closed interval that we choose will be a closed interval that's a subinterval of the interval from A to B. And we have to choose it in a way that misses big Q sub 1. And we can do this because obviously big Q sub 1 is a nowhere dense set. And we will continue doing this. So in general, if we choose I sub 2n plus 1, we can make sure that it will miss all of the sets big Q sub n because they are all going to be nowhere dense. And so by the Banach Mazur game that we've shown, we can conclude that X intersected with the countable union of I sub 1 will be non-empty. And by Cantor's intersection theorem, we can show that it will contain a point of X. And so we've won the game. And since it contains a point of X, it means that x intersected with AB will contain a point of x, and so that concludes the definition of dense. And so we've shown that x is dense, and we've proved the theorem. All right, so that was the bare essentials of the Baire Category Theorem, and I hope you enjoyed this two-part series. Thanks everyone for your time and watching. Please like and subscribe. Let me know down in the comments area what topic you would like to learn about next, whether that's math or anything in general. All right, I'll catch you next time.